For this review slide, I'd like to take a look at the analysis of heat transfer through a composite plane wall. The basic geometry of the problem is shown here. We have known temperatures at the outside walls, designated here as T1 and T2, known values of thermal conductivity for each of the walls, and known values of the wall thickness. The unknown parameters are the temperatures of the interface between the two layers and the rate of heat transfer through each of the individual layers. So in general, three unknowns. Using Fourier's law, and this time written in terms of thermal resistance, we can write an expression for QA as well as writing an expression for QB. Now, we recognize that in a steady state problem, any energy that passes, or any thermal energy that passes into layer A will have to pass through layer B. And this is going to allow us to eliminate one variable by equating QA and QB to be equal to each other. So we can write QA equals QB, which equals Q. Now this is going to leave us with one unknown, and that is going to be the interface temperature, temperature AB. And that's going to be the next step of the problem here, that we need to in other words, to enable us to find the heat rate, we need to figure out what this variable is. So our next step is to equate and solve for TAB. What I mean by equating is that we will take the right-hand side of both of these equations. So this goes here, and this goes here, and now we got to step through the algebra to solve for the one unknown, TAB. So here's our first step, our second step, and finally our third step. So again, I'm not going to take the time to go through the steps of the algebra, but they are shown here on the slide. So now we have TAB, and again, it is in terms of only known quantities right now. And again, just remember that RAB is known. It's in terms of the thermal conductivity, the thickness of the layer, and the area of the layer if we know it. If the area of the layer is not given, then the Q's here, instead of being heat rates, they become heat fluxes. So now that we have an expression for TAB, we can go ahead and plug that expression into either one, into QA or QB, because this is Q now equals minus the quantity TAB minus T1 over RA. So we'll go ahead and do that. So we're going to start from this value. And again, I'm going to drop the minus sign just to evaluate what this quantity is. Just TAB minus T1 over RA. And again, I'll show the steps, but we're essentially going through, here we've plugged in the value for TAB. Now we're rearranging, and in this case I've multiplied through by RA. And in this case, again, we've simplified terms by multiplying through by RB in this case. Now again, we're cleaning up some terms, making a single common denominator, which now allows us to combine the two parts, and now we can go ahead and we eliminate two terms and we divide through by RA, giving us our final expression. And in this case, we see that the heat rate through the composite plane wall is equal to Fourier's law, which is now modified by having a total or a sum of the thermal conductivities, the thermal resistances rather. And we can then figure out the interface temperatures, because now once we've determined Q, we can go back and rearrange these original equations to solve for temperature AB, or we could use the other equation and get it through either process, either knowing the values of T1 or from T2. And in general, for a wall of n layers, we have this expression. So again, it is the value of, it's just Fourier's law, written in terms of the sum of the total thermal conductivities. Now again, to note, if you go into your textbook, a lot of times you'll see that the negative sign has been propagated through to give this expression. And again, it is just the value of Fourier's law, but you got to mind your P's and Q's to remember that there you are doing the temperature gradient. So in this case, we are going from position 1 to position 2 from temperature 1 to temperature 2. So the gradient is written as T2 minus T1 over this total length, and the assumption is we're going in this direction. So the temperature value, if this term comes out as being positive, it means the temperature was going in this direction. And if this term ends up being positive, it's the same situation. Okay, so again, hopefully that makes sense. If not, you need to take a look at, you understand how the minus signs are being utilized in these terms, and that's the end for the review of the composite plane wall.